the Pioneer Voyager anomalies. While the outer belt argued in graphs, a different kind of whisper came from hardware built in the 1970s. Pioneer 10 and 11, little spinning buses with dish antennas, slipped past Jupiter and Saturn and kept going. Navigators at JPL listened by timing radio pings that left Earth, hit the spacecraft, and came back, a two-way Doppler heartbeat. The stakes were simple and brutal. If the numbers drifted, either our physics or our mass map was wrong. At interplanetary scale, a millimeter per second of error matters. Here's what the team saw. After they were far from the big planets, the Pioneers picked up a tiny, steady sunward acceleration, about 8 times 10 to the minus 10 meters per second squared. That's a gnat leaning on an elephant, but it was relentless. The tracking folks tried to kill it every way they knew how. Solar radiation pressure, too small that far out. Gas leaks. The spin-stabilized design didn't favor a one-way push. Software bugs, multiple independent codes agreed. In the back room, someone muttered, "Something S out there," and someone else replied, "Or something S in here." Action moved into the weeds. Every watt of heat on those spacecraft had a vector. Radioisotope generators ran hot, their warmth soaked into struts, boxes, louvers. If the heat radiated unevenly, it would push the craft, a photon rocket you never meant to build. Engineers dug up ancient blueprints and thermal vacuum logs. They modeled fins, paint aging, even the way dust might have dulled surfaces. The thermal recoil hypothesis grew teeth. When they ran the improved model against the Doppler residuals, most of the anomaly vanished into the heat, consistent with later detailed analyses that attributed the effect primarily to anisotropic thermal radiation. But here's the catch. Most is all. Even in best-fit models, some sliver of unexplained drift clung to the data, especially late in the missions when the power was lower and the geometry simpler. Was it just the last 5% of a messy thermal map, or did a residual hint at something external? The community's consensus leans thermal, but precision here is brutal. A calibration typo can masquerade as new physics, and these were one-off machines with aging quirks. Meanwhile, the Voyager's different beasts entirely were 3-axis stabilized, with heaters flicking on and off, antennas slewing and gravity assists yanking them into the deep. Their trajectories needed periodic corrections, and the tracking was noisier. Still, navigators noticed oddities. Tiny biases in Earth-based Doppler versus on-board counters, coarse tweaks that felt slightly off compared to fuel budgets, deep space tracking jitter that seemed to have a seasonal flavor, ionosphere, troposphere, station thermal flex, all suspects, pattern or noise. Most days, noise won. But in the hallways, the Pioneer story kept people cautious. If a part per billion force could slip through, what else might we be normalizing away? What nobody knew then was how the outer architecture would soon look sculpted. The idea that faraway mass might exist wasn't born from the probes, but the probes trained the culture to respect small, steady discrepancies. A discipline measures itself by what it refuses to shrug off. The Pioneer Anomaly, thermal at heart but instructive, set a standard. Prove it in the hardware before you rewrite the sky, or the other way around. Fork the road, artifact or mass. If thermal recoil and modeling imperfections explain everything, the lesson is humble. Deep space navigation is a master class in bookkeeping, and small forces add up. If any residual remains, the cleanest external culprits are gravity and drag. Drag from what? There's no ether out there, and interplanetary dust at those distances is far too thin to matter. Gravity from what? A distant, massive object wouldn't pull sunward on both Pioneers the same way unless its reach dominated the neighborhood. That raised eyebrows. A planet-sized body at a few hundred AU could leave fingerprints, but a brown dwarf or super Jupiter much farther out would act more like a slow, broad wobble on the solar system's barycenter rather than a neat, sunward tug. Action pivoted to cross-checking. Could ephemerides, our best fits to planetary positions over decades, absorb or reveal a hidden pull? Teams compared radar ranging to planets, spacecraft flyby data, and occultation timing. Any unseen mass adds a subtle bias to how the solar system dances around its center of mass. The more precisely you pin Mars, Jupiter, Saturn, and the outer moons, the less room you leave for ghosts. Constraints tighten. The parameter space for an external heavyweight shrank, not to zero, but to a narrow alley. Far, cold, dim, and lazy in the sky. Then came the discipline's quiet confession. Even if you nail the physics, the instruments carry their own weather. Earth's rotation jitters timekeeping. The deep space network's dishes breathe with sunlight and cool with night. The plasma between planets hisses on the carrier wave. Navigators live in that fog. One veteran said, "You learn to separate the static you expect from the signal you don't, and you never fall in love with either." Impact immediate. The Pioneer case didn't prove a companion, but it inoculated the field against easy answers. It showed how an unmodeled push can fake gravity and how gravity can hide behind a push. Long term, if a distant mass exists, its cleanest signatures wouldn't be a tidy sunward acceleration. They'd be timing scars spread across many systems, planet ephemeris offsets, comet delivery statistics, and the slow procession of distant minor bodies. The probes were the first nudge, a reminder to look for coherence across datasets, not drama in one. Here's a micro-story from the console. A navigator in Pasadena watches a Doppler residual drift a hair redder than expected. He rechecks the tropospheric model, swaps in a fresh antenna calibration, and the line snaps back almost. He leaves a note. Residual persists at 0.2 ms. 10 years later, that scrap shows up in a meta-analysis. It doesn't solve Nemesis. It earns the next question. And that's the pivot. If something big is out there, it shouldn't only tease the radios. It should leave marks in deep time on rocks and bones. If gravity writes, Earth keeps the receipts. We turn from dishes and Doppler to a colder ledger, the rhythm of extinction itself. The extinction rhythm, 26 million year signal. Open the rock ledger and it reads like a heartbeat. In the early 1980s, two paleontologists, David Raup and Jack Sepkoski, weren't hunting planets. They were counting funerals, compiling the most complete database of marine life extinctions anyone had attempted. Family by family, epoch by epoch, they marked when diversity plunged. Then they ran the numbers and a pattern surfaced that made geologists sit up. Sharp upticks in extinction, spaced about 26 million years apart, as reported in 1984. Not perfectly metronomic, this is Earth, but regular enough that chance started to sweat. Stakes land fast here. If life's worst days arrive on a schedule, something outside the usual volcanoes and tectonics playbook is tapping the glass. And if that schedule lines up with a long, cold orbit, we are not just passengers, we're on a route. Hook for the skeptics. If this signal fades under better dating, the whole Nemesis idea collapses. If it survives, the sky owes us an explanation. The fossil bed from our opening scene stops being a tragedy in one place and becomes one tick on a cosmic clock. Action moved from spreadsheets to mechanisms. What could swing at Earth with a 26 million year arm? The Oort Cloud, that distant sphere of icy bodies, is a loaded dice cup. Disturb it and comets rain inward. You don't need a Death Star. You need a slow, periodic perturbation that shakes the outermost orbits just enough, then steps away. Comets that survive the long fall turn into long-period visitors. A few are on collision courses. The Alvarez team's iridium layer at the dinosaur boundary had already told everyone that rocks from space can end eras. If those rocks arrive in waves, the culprit might be orbital, not random. That's where the Nemesis idea took shape. Hypothesis, not proclamation. A dim companion to the sun, maybe a red dwarf or brown dwarf, on a wide, eccentric path taking tens of millions of years to loop around. At periapsis, it passes close enough to tug the Oort Cloud's outer shells, sending a fraction of bodies inward. Earth, sitting far downstream, feels the hail. Then Nemesis recedes, the influx wanes, and the biosphere rebuilds until the next pass. Get this, people actually mapped the proposed timing of those passes against Raup and Sepkoski's cycles. It wasn't clean enough to declare victory, but it was aligned enough to pour serious attention into the sky. The companion didn't need to be bright. A brown dwarf could be almost invisible in optical light. Infrared would be the way to catch it, or gravitational breadcrumbs. But pushback arrived with scalpels, not slogans. Dating the fossil record isn't a wristwatch. Error bars stretch and compress. Some peaks moved when new strata were calibrated. Volcanoes don't care about stars, and flood basalts like the Deccan Traps can wreck climate on their own timeline. Sea level changes, ocean anoxia, plate reorganizations, each can thin life's ranks without help from the Oort Cloud. More, later analyses suggested longer cycles, around 30 to 32 million years, or multiple overlapping periodicities superimposed on a messy background. The signal was there, but its exact beat seemed to drift. And that's actually a point for orbital triggers, not against them. A bound companion in the sun's far suburbs would feel the galaxy's tides and passing stars. Its orbital period would not be a granite number. It would wander by 10, maybe 30% over hundreds of millions of years. A 26 million year average could show up as a band, not a razor line. If someone insists on perfect periodicity, they're asking the wrong sky. Meanwhile, geology brought in independent clocks. Some cores showed spikes in extraterrestrial helium-3, cosmic dust fingerprints that appeared in clusters. Impact craters on Earth are lousy timekeepers because erosion erases them. But when you stack the dates we still have, you see hints of bunching beyond random. Microtectites and soot layers point to episodes of elevated skyfall. None of these datasets alone proves a marching companion. Together, they whisper, check the cadence. Impact on the field. The Nemesis proposal didn't win a trophy, it won a to-do list. Build better time series for extinction intensity, sharpen crater dating, separate background comet trickle from shower pulses, and crucially, search the sky where a slow, cold object could hide. The controversy hardened the science. Every counterexample forced cleaner methods. Every persistent pattern bought the hypothesis one more season. Human moment. A paleontologist in a desert trench flips to a fresh page and writes, another abrupt boundary, same signature minerals, different basin. He's not thinking about brown dwarfs. He's thinking about whether the sea retreated too fast, whether the ash line came from a nearby arc. That night, someone emails him a preprint plotting his new date on a 30 million year cycle curve. He replies, could be, or could be local. Both are true until they are. There's a fork that matters. If terrestrial triggers dominate, basalts, anoxia, supercontinent breakups, the rhythm is coincidence layered over a chaotic planet. If an external trigger plays a regular supporting role, then Earth's worst days have an upstream cause that's predictable enough to watch for. Neither path excuses us from the grind of data. Both send us back to the Oort Cloud, because that's the only reservoir big enough to connect a faint, far perturber to mass death here. So does the pattern survive scrutiny? Enough of it does to justify a renewed search. Not a proclamation, not a press conference, just the next round of hard constraints. If a companion exists, its orbit must be wide, its light faint, and its influence seen more in timing and geometry than in photographs. Infrared eyes have something to say about that, and their silence is the infrared ghost clue. If a companion hides in the dark, infrared is where you corner it. That was the bet. Brown dwarfs don't shine like stars. They glow with leftover heat, cool embers in a cold room. So we built eyes for heat. The 2-micron all-sky survey, 2MASS, swept the heavens. Then WISE, the Wide-Field Infrared Survey Explorer, mapped the sky in 4 infrared bands with a sensitivity leap that should have snagged many warm neighbors out to several light years. Stakes couldn't be clearer. If Nemesis glowed, WISE would have had a fair shot. Here's the catch. Brown dwarfs cool with age. A young one might be toasty enough to pop in near-infrared. An old one sinks to a few hundred Kelvin, radiating mostly in the mid-infrared, dimming hard with distance. And luminosity falls off as the square of distance, so every extra AU is a tax on detectability. WISE did pull in a trove. Why dwarfs so cold some were not much warmer than room temperature, and a near-complete census of warmer brown dwarfs within a few parsecs. The result many took as a verdict: no obvious nemesis in the backyard. But verdicts need footnotes. WISE's completeness tails off for the coldest, faintest objects, especially if they move slowly enough that they don't betray themselves with big proper motions between survey passes. A companion on a multi-100,000-year orbit would crawl against the stars. If its temperature sat at the low end, say a wide dwarf colder than expected, or if it sat well beyond 1,000 AU, its flux could slide under the noise floor. Add in confusion. Near the galactic plane, the sky is crowded with infrared sources. Distinguishing a faint, slowly drifting ember from a distant galaxy or a mottled patch of cirrus is not trivial. Action moved to constraints. Astronomers used WISE and two masks together to search for high proper motion cold objects. They found many, and in doing so they boxed the parameter space hard. Within tens of thousands of AU, anything the mass of a typical brown dwarf, warmer than a few hundred Kelvin, and not hiding right in the glare and confusion zones, should have shown up. That shrank Nemesis from any dim star to extremely cold, likely very distant and maybe lower mass than a star, a super Jupiter or a borderline brown dwarf. Non-detection wasn't a kill shot, it was a corral. Meanwhile, instrument people whispered about floors and ghosts. Infrared detectors carry quirks, latents from bright sources, band-to-band color terms that can misclassify a weird spectrum, and calibration drifts that live at the edge of faintness. Teams combed the catalogs for outliers with odd colors that didn't fit standard templates. Some were artifacts, some were galaxies, a few were real ultra-cool dwarfs. None screamed solar companion. Loopholes stayed on the table. Put the object on a high-inclination orbit well out of the ecliptic, and the all-sky coverage is still there. But follow-up can lag because most survey pipelines and ground campaigns concentrate near the ecliptic where most moving objects live. Push the period long, the motion slow, the temperature low, and a real thing can look like a barely moving speck whose color mimics a distant galaxy's dust glow. And the further you shove it, 50,000 AU, a quarter of the way to the Oort Cloud's edge, the fewer photons you get, no matter what. Human moment. In a small office, an astronomer clicks through WISE codes, eyes aching at the grain. There's a source that's just above the threshold in W3 but barely there in W2, nothing in W1. Over 5 months, it shifts by a fraction of an arcsecond. She flags it, writes possible cold HPM, and sends it to a colleague. The reply a day later: galaxy, extended in deeper stack. She sighs, opens the next tile, and keeps hunting. Meanwhile, other constraints piled in. If a massive body lurked at a few thousand AU, its gravity would tug planet ephemerides measurably. We don't see that. If it were a normal M dwarf within a light year, even dim, it would have been catalogued ages ago. WISE's null means a traditional, bright nemesis is off the board, but the universe is generous with gray areas. A low-luminosity companion, massing more like a super Jupiter or a cold brown dwarf, tucked beyond a few thousand AU, remains a mathematical resident in the model's spare room. Therefore, non-detection narrows properties. It doesn't kill the idea outright. It tells us any companion must be faint, cold, distant, and slow. It points to where to look smarter, not louder, stacking epochs to tease motion, cross-matching colors to isolate non-galactic spectra, and leaning on astrometry to catch reflex wobbles instead of light. Infrared didn't slam the door. It made the hallway narrower. Impact ripples through the narrative. Infrared silence shifted the search from spot the ember to prove the pull. If light won't volunteer, geometry has to testify. That loops us back to the outer solar system's architecture because there's another clue baked into the orbits themselves. The Kuiper Belt isn't just clustered, it's tilted, warped in a way that suggests a long, patient torque from something inclined. If the sky won't show us a face, maybe the disk can show us a handprint. The tilted outer solar system. While infrared kept us guessing, the orbits started talking. The ecliptic is our baseline, the tabletop of the inner planets. If that table is warped out where sunlight fades, something's been leaning on it for a very long time. Stakes don't get more basic. The plane of the solar system is our reference frame. If it's tilted in the outskirts, every model of how our system formed and settled needs a rewrite. And if the tilt has a preferred direction, it could be a fingerprint. Action first. Astronomers mapped distant trans-Neptunian objects and noticed the mean orbital plane beyond roughly 50 to 100 AU sits a few degrees off the inner system's plane. Not just a random scatter, an organized offset, with hints that the outer disk is slightly twisted, like a vinyl record left in the sun. The effect is subtle. You don't see it by eyeballing a handful of icy rocks. You need a census, careful bias corrections, and simulations to ask, could random discovery angles fake this? The answer keeps coming back the same. Bias can nudge numbers, but it doesn't easily manufacture a coherent warp. Here's where mechanism matters. Torque builds slowly. An inclined perturber, massive enough to matter, far enough not to wreck everything, can, over tens to hundreds of millions of years, tilt the average plane of distant orbits. It doesn't need to be dramatic. A few degrees is huge when the only other actor is Neptune, which tends to flatten, not twist, on long timescales. If you run n-body simulations with a distant, inclined mass, the outer disk's mean plane precesses and settles into an offset, a quiet compromise between Neptune's tug and the distant hand. Take that mass away, and the disk relaxes closer to the ecliptic, drifting without a stable, coherent tilt. Stakes human side. If a companion is doing this, its torque is writing geometry as patiently as ice carves valleys. That's testable. Track the mean plane region by region, 50 to 80 AU, 80 to 150, out to the detached objects, and watch how the tilt and node drift with distance. A companion's influence should increase and then fade in a predictable way, depending on mass and separation. Neptune's history can mimic some of this, but not all, especially for bodies that barely feel its resonances. The further out you go, the less Neptune owns the dance. Complications cut in hard. Microperturbations, cumulative nudges from countless small bodies, can, in principle, create a statistical warp if the disk is clumpy and long-lived. Past migration of the giant planets might have left a kink, a fossilized wave in the orbits. And selection effects bite again. Telescopes hunt near the ecliptic, so we see more objects where we look more. Teams fight that by modeling survey footprints and reweighting the sample to unsee their own habits. Even after that, the tilt doesn't vanish. It softens, but it stays. Meanwhile, something else was happening in the data. The tilt's line of nodes, the direction where the warped plane crosses the ecliptic, isn't random either. For subsets of distant objects, those node longitudes cluster more than chance suggests. That's geometry you can't hand-wave away by saying, "We just didn't look over there." If the warp and its orientation persist as the census grows, you're not just seeing a bump in the carpet, you're seeing a handprint. Here's the late-night human moment. An astronomer, 3 coffees in, redraws the average plane for a subsample that excludes obvious resonant objects. The line she gets points almost, but not exactly, where last month's run pointed. She mutters, "Too neat," saves the file, and runs a jackknife, dropping chunks of the sample to see if one survey field is steering the ship. The plane wobbles, then returns. She writes, "If bias, then elegant," and closes the lid at 2:17 a.m. Simulations step in as referees. Put a super-Earth at a few hundred AU on a modest inclination. You can torque the outer disk by a few degrees and reproduce some clustering features. Push the perturber farther and heavier, a super Jupiter or a cold brown dwarf in the low thousands of AU on a tilted orbit, and the torque becomes broader, slower, and less likely to oversculpt the inner Kuiper Belt. Over gigayear timescales, that companion slowly twists the mean plane and sets a preferred node. Take care, though. Make it too massive or too close and you scramble known orbits, a violation the ephemerides won't forgive. Impact lands in 2 places. First, the geometry rhymes with the gravitational lag and the extinction cadence, a long, patient torque in space, and a slow rhythm in time. That doesn't prove a binary sun, but it keeps the door open in a disciplined way. The warp is a measurable secular effect that a distant, dim companion could explain without lighting up the sky. Second, it forces a duel with a rival story, Planet 9. A single massive planet, lighter and closer than a star, can explain much of the clustering and some tilt, especially in the 200–600 AU zone. A star-like companion, heavier and farther, better explains a uniform, gentle warp spanning wider distances and leaves room for deep-time comet modulation. Therefore, the test sharpens. Watch the mean plane as new distant bodies are logged, especially at the extremes, the truly detached Sedna-like worldlets and objects beyond 150 AU. Measure their node precession rates. If the warp strength and orientation evolve with distance the way an inclined, far companion predicts, the case strengthens. If the tilt collapses under an unbiased census, bias wins and the shepherd dissolves. Everything is about to change when we pit twin against planet. Planet 9 won't go quietly, and neither will a conservative nemesis. The only way forward is prediction that one can't fake. Planet 9 versus Nemesis, comparison test. While the outer disk whispered, "There's a hand on the table," the room split over who owned the hand. One camp sharpened Planet 9, the other kept the dark twin on the board. Stakes couldn't be higher. Choose the wrong culprit and you waste a decade of sky time and simulations, and you train students to solve the wrong puzzle. Start with Planet 9's clean story. Put a super-Earth, say 5 to 10 Earth masses, on a distant, elongated orbit with a semi-major axis of a few hundred AU and an inclination of maybe 15 to 30 degrees. Give it a perihelion far enough from Neptune to avoid chaos. In that setup, the planet shepherds the long axes of extreme trans-Neptunian objects, anti-lining many of them with its own. You get clustered perihelia, a preferred set of node longitudes, and even a population tilt for objects whose orbits are detached from Neptune. In simulations, the effect shows up in millions of years and can persist for billions. It's a tidy fix for the flock we see. Now the dark twin Nemesis asks a different service. It doesn't explain tight local clustering as efficiently. Its strength is slow, system-wide torque and deep time pacing. Imagine a body far heavier than a planet, super Jupiter to brown dwarf, parked not at 400 AU but in the low thousands to tens of thousands of AU on a long, inclined, eccentric orbit. Its light is faint, its motion is glacial, but its gravity writes in broad strokes. Over huge spans, it leans the mean plane of the outer disk a few degrees and, crucially, periodically stirs the Oort Cloud enough to juice comet delivery. It trades surgical clustering for a metronome and a warp. Here, that's where the duel gets practical. Prediction that one can't fake. Planet 9, if it exists, must sit in a specific swath of sky that produces the observed anti-alignment. That means it predicts not just the general clustering, but the distribution of orbital poles and perihelion longitudes for newly found distant objects. As new TNOs stack up, Planet 9's gravity demands their arguments of perihelion process at rates tied to its mass and distance. Teams have published corridors on the sky where a dim, slow-moving object should lurk, waiting for lucky seeing and deep exposures. Nemesis counters with different receipts. It says, measure secular precession of the mean plane itself as a function of distance, 50 to 80 AU versus 100 to 200 AU, and look for a gentle, coherent drift in node directions that's too uniform and too extended for a single 510 Earth mass planet to produce. Then go to time, long period comet flux. If a companion's orbit brings it closer every few tens of millions of years, we should see comet injection windows, clusters in arrival epochs that beat against a galactic tide background. That's not a backyard telescope test. It's a database fight spanning centuries of comet detections and millions of years of crater and isotope clocks. Complications slice both ways. Planet 9 faces infrared and optical non-detection so far, but at a few hundred AU and Neptune dark, A small, cold super-Earth could be invisible in broad surveys and only betray itself by motion in deep, repeated imaging. Nemesis faces Ys and two mass nulls, yet a very cold, distant, substellar object could stay below those floors while still being massive enough to torque planes slowly. Planet 9 must leave tighter signatures in the orbits of known TNOs, specific secular frequencies and resonant captures. Nemesis must not wreck ephemerides or pop out in Gaia's census of local brown dwarfs, so its parameter box squeezes toward colder, fainter, and farther. The testable roadmap takes shape. First, track specific TNOs, Sedna-like and beyond, for minute changes in their longitudes of perihelion and node over the next decade. Planet 9 predicts a pattern of precession rates and resonant trapping that a diffuse, far torque can't mimic at that strength and speed. Second, expand the deep TNO census off the ecliptic and into the southern winter sky where many surveys are shallow. Correct the biases and see if the clustering persists. If it dissolves, both models lose a pillar. If it hardens with new, well-characterized discoveries, Planet 9's odds improve. Third, quantify the outer disk's mean plane tilt as a function of semi-major axis with error bars that include survey footprints. A gentle, monotonic warp argues for a far, heavy hand. A sharper, localized distortion nearer a few hundred AU fits a planet. Fourth, build comet flux statistics that separate selection effects, modern survey sensitivity, hemispheric telescope bias, from true long-period arrivals, then cross-check against terrestrial proxies like helium-3 spikes and crater date clusters. If arrival windows line up with a plausible Nemesis period band, that's weight Planet 9 can't claim. There's a wild card. Both could be partly right. A single distant planet could sculpt the inner extreme TNOs while a much farther, colder object applies a slow torque and sets the deep time metronome. The parameter space for that duet is tight. Ephemerides and infrared limits cut deep. But tight isn't empty. Human moment. A grad student overlays predicted precession tracks for 3 TNOs under a 7 Earth mass Planet 9 and under a 0.05 solar mass brown dwarf at 8,000 AU. One set curves fast and diverges. The other barely bends but stays coherent across distance. He circles the divergence and writes, "There, that's the bet." Therefore, the comparison isn't about belief, it's about forecasts with teeth. Planet 9 must call its sky square and the way new orbits will line up. Nemesis must call the warp slope and the timing of the next comet bump. Over the next observing seasons, those are numbers we can watch. Oort Cloud mechanics and comet showers. Follow the pull all the way out and you hit the Oort Cloud, the dimmest, loosest border of home. Stakes are blunt.